In the last lecture, actually, we discussed about the discrete random variables and we have done some problems. So today we will discuss about the continuous random variable. So we are going to talk about the continuous random variable. Okay. Continuous random variable. Okay. So you can see that in discrete random variable, the number of outcomes basically was finite, or it was the set of all outcomes was a countable set. But here it is not a countable set. For example, it can be a real line. For example, the real line, you know that it is not countable, because if you take any point in the real line, you know that if you take any point, let's say x, x1, and if you take any point x2, between this x1 and x2 you can find infinite number of points. That means you cannot assign a real number, you cannot assign a natural number for each element. It's difficult. That's why it is not a countable set. That's why there are a lot of that's why we use the notion of sigma algebra for this representation also. So anyway, first of all, I will discuss about the continuous random variable. That means the number of elements or the number of outcomes, we can say the number of elements in the set is not finite. So you know that what is a random variable? Random variable, basically each outcome in a random experiment has been mapped into a real line, right? Into a real number. That's it. That is known as a random variable. That's what we have already discussed. That means the random variable is nothing but a random variable x is a function. Actually, basically it is a function. It is a function that assigns a real number, right? It assigns a real number, which it is nothing but real number x of zeta to each outcome. To each outcome. That's what the definition. Each outcome that we have already seen. That means if you have a sample space and zeta is an outcome, and this zeta will be mapped into a real line, right? Real line. So basically, suppose if you are this set, for example, this is the sample space in X. If this set is finite, or countably finite or countable, then we will say it is a discrete random variable. If it is not, if it is not finite or not countable, then we will say this is the continuous random variable. Okay, so we are talking today about the continuous random variable. So this is the continuous random variable. That means, suppose if you take any points on this, okay, let us assume that you take any points on this. If you take any points, let's say you have x1 and you have another point x2, between this x1 and x2 you can find infinite number of points, right? Infinite number of points you can see. So in continuous random variable, the set is actually, set contains infinite number of points. Okay, it's not countable anyway. So in order to deal with this, first of all we will discuss about the distribution function. So we are talking about the cumulative distribution function, okay, or the probability distribution function. So in the case of the discrete random variable, we discussed about the cumulative distribution function. You know, in discrete random variable we talked about the cumulative distribution function and the probability mass function. Okay, I hope that you know the clear difference between these two. Okay, and this is nothing but the probability that the random variable x takes the value which is x less than or equal to some x, okay, and this is nothing represented as fx of x, and this is the probability mass function. It is nothing but px. It is the probability of each event in that random of the random variable. Okay, we are talking about the random variable now. So this is the case of discrete. Okay, discrete. Now we will talk about the continuous random variable. Okay, so in the case of the continuous random variables, continuous random variable, that is CRV, okay, I will use the abbreviation CRV, then we can define the distribution function, okay, the probability distribution function. It is also known as the cumulative distribution function, as you talked about the discrete random variable. So it is the cumulative distribution function. It is again, it is nothing but the probability that the random variable x takes the value which is less than or equal to x, and it is usually denoted as fx of x, okay, as in the previous case. So it is same like the previous case, okay, but there is a difference in the PMF. Actually there is no PMF here. It was probability mass function, but here there is, we cannot point out the probability for individual things. For example, if you have a real line and if you take any point x, you cannot assign any probability directly for point x as p of x. This notion will make a problem because there are infinite number of points, and then it's very difficult to assign, and if you sum all the probabilities it becomes 0. That we have already discussed in the lecture 2. So what I want to tell is that instead of the cumulative, instead of this guy, that means the probability mass function, instead of this we have in the continuous random variable something different, which is known as the probability density function. Okay, this is what we have in the continuous random variable. That means it is defined as f small x, fx of x. Okay, so instead of the each individual probability, we are defining a function which is a density. You know that what is the notion of a density? Actually this is known as the probability density function. Density means actually, you know, it is mass per unit volume. Basically the density was is a notion in the material science. You know that it is mass per unit volume. If you know the mass per unit volume, then you can find the actual mass by multiplying with your for example, this is a material, for example. Then what is the notion of density? Actually it is the mass per volume, right? That is the density. That's usually denoted as rho. That is, rho is actually mass by volume, and its unit is kilogram per meter cube. And if you take a small piece from this, if you consider a small piece from here at this portion, if you consider a small piece, then you can find what is the mass of this small portion. Let's say this is a small portion delta m. Okay, the mass of this you can find it by, you can multiply the density with the volume of this. Suppose it is having a volume delta v, then you can find it by delta m is equal to the density into volume. So this is what the concept of density in material science, you know, material science. Okay, in physics, you can say in general physics, okay, in physics. But here, okay, but here we are also talking about the density of the probability, how dense the probability. So if we take a range, if you take a range, then you can find it, you can find the actual probability also. So this is known as the density. So I will discuss it in more detailed way. What is the relationship between this density and the distribution, cumulative distribution, okay, probability distribution function. So this is also known as, I told you, its probability distribution function is also is cumulative distribution or probability distribution function. You see that I have used the capital letter, and this is usually denoted as small letter PDF, okay. So in some textbook you can see that they have used everything in a messed way. Anyway, for throughout this course we will use this notation. PDF means, capital PDF means probability distribution function or cumulative distribution function, and small pdf means actually it is the density function. So the probability, sorry, the probability distribution function, okay. So we are talking more detail about this, of the continuous random variable, okay, of continuous random variable. So the fx of x is nothing but the probability that x, the random variable x, takes the value less than or equal to x. The meaning is, it is the probability that the random variable x takes the value less than or equal to small x. That is the meaning, okay. So this is showing the random variable, and this is the value taken by the random variable. X is the value taken by the random variable, and x is the general notation for the random variable, okay. So if you want to find, for example, okay, then that is fx of w is nothing but the probability that the random variable takes the value less than or equal to w. That's it. This is the general idea actually. So we will do some problems inshallah later. Now I want to clarify some properties of this as follows. Before that, I will introduce you the concept of probability density function also. Probability density function, okay. Probability density function, this is nothing but the PDF, small letter PDF. So if you read the research articles, journals, you can find this. So the definition is nothing but the PDF, usually denoted as fx of x. You can see it is using small letter. So fx of x is defined as d by dx of fx of x. It is nothing but the d by dx of fx of x, okay. That means you have to just take the derivative of this, okay. And this is nothing but the PDF of the random variable x. This is nothing but the PDF of the random variable x, okay. Now you can find the inverse relation. You can find the fx of x. How to find? If it is the derivative, then you have to just integrate minus infinity to x fx, sorry, small fx of x. So if you integrate the fx of x dx, then you will get the PDF. This is your capital PDF, okay. The probability distribution function is the distribution, okay, distribution. So this is the distribution and this is the density, okay. So don't confuse. So if you integrate the density, then you will get the whole distribution. That's it, okay. So we will see some important properties of the cumulative distribution function. Okay, so this is also known as, I told you, it is also known as cumulative distribution function, CDF. Okay, oh sorry, I have made a mistake here. Okay, this is also known as, this is the cumulative distribution function. Okay, CDF. In some textbook you can see it is also PDF. So this PDF means it's same as CDF, it's just another word. Okay, and this is the PDF. Okay, the probability density function. Okay, so we will see some properties of this CDF. Okay, so we will talk about the properties of CDF. So we will discuss about the properties of CDF. You can see that the first property is given here. That means it is nothing but the CDF is a function which is always having a value between 0 and 1. So what does it mean? Actually, you know that the maximum probability, CDF means actually the sum of all probabilities, because the CDF fx of x, I told you, it is defined as the probability that x less than or equal to some value x. So you can see here, if you take any value minus infinity, the probability that x less than minus infinity, that means the probability that x less than minus infinity, it is 0 actually, nothing now even there. Now as you move on, suppose if you take any point A1, then A2, like this, A3, let's say this is 0, this is A4, let's say A4, and this is A5, and this is A6, and so on, and this is at infinity. So the probability that x less than infinity is basically, it is 0. Now what is the probability that x less than A1? That means the probability that x less than or equal to A1, there is some probability, let's say it is P1. Okay, then if you take any point A2, after A1 you have to take, suppose you take any point A2, then it is nothing but P2, that is the probability that x less than A2. That means if you take the point A1, you may get the value as P1, but if you take the point A2, you have lot of points in between A1 and A2, so you have to take into account all these probabilities. That means you will add all these probabilities together. So definitely your P2 may be greater than or equal to P1. That means it is because you have lot of points in between A1 and A2, so your P2 will be greater than or equal to P1. So let us assume that here it is P2. Similarly, if you take A3, you may get little bit more sometimes. Maybe sometimes it will be same also, but you cannot say that P2 is less than P1. It will never happen. Okay, so if you do like this, if you take all these points, you can see here your cumulative distribution function. In most of the cases, it will take the shape like this, many cases. Okay, and finally, when you take any point infinity, that means the probability that x less than or equal to infinity means what? You have a region which is completely, this is the probability that x less than or equal to infinity means x take any value below infinity. That means you are considering all the region, that means its probability is 1. So the cumulative distribution function actually it goes to 1. Okay, maximum. So it is starting from 0 and it is having a maximum value 1. That's what the first point. Okay, so now as x tends to infinity, this is the second point, as x tends to infinity, that means x tends to infinity, the probability that fx of x as x tends to infinity is equal to 1. That means the probability that x less than or equal to infinity such that your x is tending to infinity, it is nothing but, I told you, now if you are at infinity, you have to consider all the points before infinity. Okay, so less than or equal to infinity, then of course you are considering all the sample space of the random variable, then the probability is equal to 1. Now as x tends to minus infinity, as I told here, okay, as x tends to minus infinity, you can see here this value, actually if there is nothing before infinity, minus infinity, so this value is going to 0, right? So that is the, and I told you fx is a non-decreasing function of x. That means you can see here always it is increasing. It may be constant sometimes, but it may be constant or it may be increasing. It will never decrease. It is always an increasing function. So that is the fourth property. Okay. Now you can have another formulas here. This is another very important property. The probability that the random variable x takes the value between a and b is nothing but f of x minus fx of b minus fx of a. So we can easily find it. That means I can give the proof of this. That is the probability that a less than x less than or equal to b. How to find this? It is nothing but the probability that, you see here x is greater than a, okay, x is greater than a. So this I will just draw a cumulative distribution function for your convenience. It is taking a value like this. This is fx of x and this is your x. Okay. Now you see here the random variable x takes the value which is less than b. Okay. So you can consider here, for example, b. It is less than b, but you see if you read like this, it is greater than a. So it is a is here. Okay. A is here. That means you want to find the probability that your random variable takes the value between a and b. This is between a and b. Between a and b. So what is your fx of b? Fx of b is nothing but, you are considering all the region till b. That means it is nothing but fx of b means what? Fx of b means it is nothing but okay, fx of b means it is nothing but the probability that x less than or equal to b. Now fx of a, what is that? Fx of a is nothing but the probability that x less than or equal to a. Then less than or equal to a, b means what? It is the points from minus infinity to b, right? And less than or equal to a means the points from minus infinity to a. So if you want to find the points only between a, b and a, what you have to do? You have to take fx of b, then subtract it from fx of and subtract fx of a from it. Okay, then you will get the points between the a and b. So this is the probability between a and b. Okay, a less than x less than or equal to b. So that is what the sixth point. Okay, and the seventh point, then the fx of at x is equal to b, then fx of b at x is equal to b, then what is the probability at x is equal to b? So we will see here the seventh one. That means the probability that x is equal to b means what? We know that fx of b is equal to, okay, it is nothing but the probability that x less than or equal to b. You can see there is an equality here. Now fx of b minus is nothing but, b minus means if you take any point b, then b minus means what? It is just the point which is very close to the b but to the left side of b. Okay, it is nothing but the probability that x less than or equal to b minus. So b minus doesn't include b, it is the closure. We will call it as the closure. It's the closest point anyway. It is known as the closure, you can say. Anyway, I'm not going to use those technical definition, not to make you confused anyway. So if you subtract these two, that means if you take fx of b and remove fx of b minus, because b minus include all the points from minus infinity to b minus, and fx of b means you have all the points from minus infinity to b. So if you subtract these things, that is fx of b minus fx of b minus, then you will get the probability that x is equal to b. Okay, this is how you can find this probability. Now next is nothing but the probability that x greater than x. What is that? You know that fx of x, what is the definition? It is nothing but the probability that x less than or equal to x, right? So it is nothing but the probability that x less than or equal to x. Now if you take the distribution, it will usually take a form like this. So if you take any point here x, then this is nothing but the probability that x less than or equal to x, and this is your distribution function. Okay, now if this is the value here, okay, this is the distribution function for x, okay, fx of x. Okay, now if you want to find this fx of x, now if you want to find the other part, okay, so this part is showing the distribution function fx of x, then what will be this part? It is nothing but the probability that x greater than or equal to x. So you know that what will be this part, because you have a maximum value of 1 anyway, because the distribution function will be having the maximum value 1. So this part is showing actually this part is showing your fx of x. So what will be the next part? The next part will show it's the probability that x greater than or equal to greater than x. So this probability that x greater than x is nothing but 1 minus, because the maximum value of the distribution function is 1. So you are talking only about this part. So this part is nothing but 1 minus fx of x. Okay, I hope this is clear to you. So we have got the different points. Okay, now we will see a problem based on this. So this is example 4.2 from the textbook. So you can you have a arrow which is spinning. I will just draw here, which is spinning at the center of the circular board. Okay, so there is a circular board, you can say. You have a circular board, and at the center there is an arrow, and this is spinning like this, and you are measuring its angle. Okay, you are measuring its angle. Suppose the angle, it is theta here. That means you have a 0 angle here, and you have pi, and okay, so this is the direction of spinning. So you have 2 pi here, right? So this is, so your theta actually changes from 0 to 2 pi. Okay, so if you rotate this, suppose one person is standing here and he rotate this, okay, with his hand, then you can measure the probability. What is the probability that it takes the value between 0 and 2 pi? Can you tell me? That means you have a spinning arrow which is having an angle theta here, and this is pi, and this is again 2 pi. So what is the probability that it takes any value between 0 and 2 pi? Probability that it takes value between 0 and 2 pi. That means, of course, you can get any value between 0 and 2 pi, because if you rotate it, it will be at any position, maybe at 0, maybe at pi, maybe at pi by 2. This may be pi by 2, this is 3 pi by 2. So it may be, it will be at any position anyway. So this probability is 1. That means you can expect any value, okay, you can expect any theta, okay, between 0 and 2 pi. Let's say this random variable is denoted as x, then what is the probability that x less than or equal to 2 pi? You can take any value, you can get any value from 0 to 2 pi, that is nothing but 1, right? Now, what about the probability that what is the probability that x less than or x takes the value which is less than or equal to pi? Can you tell me what is the value that the probability that x takes less than or equal to pi? So how to proceed with this? The probability that x less than or equal to pi. Yes, of course, you will get half, right? You will get half, because the total probability to be anywhere between 0 and 2 pi was 1, and this is half of that part, so it is half. Can you next, what is the probability that x takes the value less than or equal to pi by 2? That means if you consider this part, it is nothing but 1 by 4th of that circle. So what you can do, how to assign the probability distribution function for this? The probability distribution function, so then what is the probability that x less than or equal to theta? Let's say you assume an angle theta here, then what is the probability that x takes the value which is less than or equal to theta? Okay, what is that probability? The probability is nothing but, you have the 2 pi means you are mapping it into 1, right? Then what will be the theta? Because for 2 pi, for x less than or equal to 2 pi, you are assigning the value 1. I told you that it's the whole space. So for theta, what will be? So you have to use the simple mathematics. For theta, you can find this value as theta divided by 2 pi. Okay. So it is nothing but theta by 2 pi. This is the probability distribution function. So the probability that x takes the value which is less than or equal to theta is nothing but theta by 2 pi. Okay. Now, so you can actually assign like this, and you have something like between it is nothing but 0 and 2 pi. So what is the probability that x less than 0? It is nothing but sorry, I will use here, I will use the next page. So the probability that x less than or equal to theta is nothing but theta by 2 pi. Now you see here, this is 0 and this is 2 pi. Okay. Okay. Now you can see here that your random variable takes the value, what is the probability that x less than or equal to 0? Okay. There is nothing before 0, so all these probabilities are 1. Now you can see here the probability that x less than, if you take any value theta here, the probability that x less than or equal to theta is nothing but theta by 2 pi. That means it is directly proportional to theta, or it is a linear function. It's a linear function. You can see it is a linear function of theta. So this is nothing but it is a linear function. It's a linear function of theta. Then when it reaches 2 pi, the probability that x less than or equal to 2 pi is nothing but you have to substitute here 2 pi for theta divided by 2 pi. So it is nothing but 1. So at 2 pi it will become 1, and after that actually it's always 1. So this is the cumulative distribution function in terms of theta, you can say. Okay, I will use the notation theta here. Sorry, did I use any word? Okay, so this is a cumulative distribution. Yeah, it is a cumulative distribution function. Okay, x, you can also use x. Okay, x theta I will use. Okay, x theta everywhere. Okay, now x theta. Now in the textbook they have also given one example, another thing. That means they have also defined a random variable in another way. That means they have defined a random variable x also, and x takes the value between 0 and 1. Okay, so x, they have defined a random variable in another way. That means it is between a random variable which takes the value between 0 and 1. So that also can be done. Okay, so that you can read and understand. It's not a big deal anyway. So in this case you can see here our random variable is having a distribution. Now I told you what is fx of x. If you fx of x is nothing but the derivative of fx of capital Fx of x. So this is a straight line, you can see, straight line, and here it is 0 anyway, and here this is a constant. So I will consider the first part. So if I take the first part, you can see here what will be, it is 0. So at 0 it is 0. Now at 2 pi, from 2 pi onwards it's a constant. If you take the derivative of a constant, again it will be 0 here. So this will be 0 here, and here it will be 0 here. Now between the 0 and 2 pi, what will be the value? Between 0 and 2 pi, you take the derivative, because fx theta of theta is nothing but theta by 2 pi. You take the derivative of this. If you differentiate, it's become 1 by 2 pi. You see here, it's 1 by 2 pi. That is nothing but d by d theta of fx theta of theta. Okay, this is, so this is nothing but your PDF fx of x. So it is between 0 and 2 pi. So it is a constant which is nothing but 1 by 2 pi. So how to find this constant? It's without differentiation itself. You can see that this is a linear graph. Because of this linearity property, you are getting a constant in the PDF. So this is nothing but the probability density function I told you. So this is the probability density function. So I will use the next page anyway. So you have 0 and 2 pi, and it was like this. This is a linear graph, and this was your fx of x. Okay, fx of theta, fx theta of theta, and you are getting something like a linear graph like this. This is your cumulative distribution function, or the capital PDF. Okay, then if I differentiate, then what I am going to get is I am going to get a graph like this, 0 and 2 pi, which is a constant, and this is, so this is the fx of x theta of theta. Okay, let me what I have, okay, fx theta of theta. Okay, so you can see here this is fx theta of theta. So this is the idea of the PDF. Now if you take any value, this is your theta, okay. If you take any value here, let's say this is your theta 1, then how to find the fx theta of theta 1? It's very easy. You have to add, it is nothing but the probability that x theta less than or equal to theta 1, right, by definition. So this is nothing but you have to add all these probabilities. That means you have to integrate all the probabilities, that you start from minus infinity to that theta 1, okay. You will start from minus infinity to theta 1. You will integrate under the curve fx of theta and to d theta. That's it. So if you find this area is nothing but fx theta of theta 1. Okay, we will discuss this later anyway. Now we will see more on the probability density function. Okay, so the probability density function, okay, we will see more on probability density function. I told you fx of x in general is nothing but fx of x, you have to differentiate with respect to x. This is your fx of x, this is by definition, okay. Now how to find fx of x? It is nothing but integral minus infinity to x fx of x, sorry, not, it's small fx. If you integrate the small fx till the value of x, then you will get fx of x. But you see here in the integration and the variable I am using the same x, so it is not a good notation, so I will change it anyway. So I will use another notation, that means I will use the variable t here for the integration. Finally I will put the limit as x, okay. This is my limit, okay. So in the previous case, in the previous example, I told you about this PDF was between 0 and 2 pi, and it was 1 by 2 pi. It was the amplitude here, you can see, and this is your fx of x. Now for any value of theta 1, let's say this is theta, then fx, this is fx theta, then fx theta of theta 1 is nothing but the probability that x takes the value which is less than or equal to theta 1. This is the definition. It is can be given by just finding the area under the curve, just finding the area under this curve till theta 1, okay. You will start from minus infinity, but for this particular curve you cannot see anything here, everywhere it is 0 here, okay. So you just need to take the area under the curve at this particular portion. That means integral 0 to theta 1 fx theta of, okay, this is theta, so sorry, theta, f is theta, okay, then theta into d theta, okay. That's it. So this is how you can find the distribution function. This is the cumulative distribution function from the PDF, and this is the PDF, okay. And you can see here in the above problem, means actually the problems that we have discussed, just before now, okay. So in this example you can see here this is a constant, the density is constant, that means the PDF is constant, or we can say it is uniform, it is same everywhere, uniform throughout, right, throughout. So this kind of density function is known as uniform distribution, or we can say it's density basically, but usually we will call it as uniform distribution, okay. So it is basically coming from our distribution. So this is nothing but the uniform distribution, okay, uniform distribution, okay. So we will call it is basically it is a density function. The density function is uniform. So when the density function is uniform, then we will call the distribution as uniform distribution. Okay, so this is the uniform distribution. So in uniform distribution, in general, we have something like this. You have this point A and B, okay, and this will be the shape fx of x, and this is your x as the random variable. And I told you the probability that x less than or equal to infinity is nothing but fx of infinity, okay. It is nothing but integral minus infinity to infinity. That means you have to take the whole curve, okay, minus infinity to infinity fx of x dx. I told you the probability that x less than or equal to infinity means you are considering the extreme point. At extreme point the value was 1, so this value will be 1. So what does it means? This is nothing but the area under fx of x. So the area under fx of x will be always 1, okay. So the area under fx of x will be always 1. So if you take the whole area, this area is equal to 1, then what will be the amplitude? Because you know this width is actually b minus a, so b minus a into this amplitude into amplitude is nothing but your whole area, right, of this particular curve in uniform distribution, okay. I am talking about uniform distribution, okay. So this is equal to 1, and this equation is valid for any distribution, actually any distribution. So this is valid for any distribution, when this is a general notion anyway, okay. So the area is equal to 1. So what will be the amplitude? The amplitude will be equal to 1 by b minus a, okay. So this amplitude, actually basically this amplitude will be 1 over b minus a, okay. This is the idea of the PDF, and this is the uniform distribution. Now we will see some properties of the PDF. So we will see some properties of PDF. The properties of PDF, the first property, fx of x is always greater than or equal to 0, because the density function will be never negative, because our probabilities are not negative. The second property, if you find the whole area, that's what we have just discussed now, then fx of x is nothing dx. If you integrate the whole area, that means area under fx of x, it is always 1. It is nothing but the fx of infinity. It is nothing but the probability that x less than or equal to infinity, okay. Next, fx fx of x is piecewise continuous, okay. Piecewise continuous, it's always continuous function, okay. Piecewise also. Next property is very important property, the probability. If you want to find the probability of a random variable x between the points a and b, then what you have to do, you just need to integrate from the point a to b fx of x dx. Okay, that's what. Suppose if you have a uniform distribution, if you have anything like suppose your fx of x is like this, it may not be uniform. This is not uniform, non-uniform. Okay, non-uniform. You can see here, this is your x. Suppose you have a point A and you have a point B. Now if you want to find what is the probability that the random variable x takes the value between A and B, then what you have to do, just integrate between A and B. That is the advantage. So instead of talking about the probability in a very conventional way, if we have a density function, it's very easy to handle the probability. That's why it has been introduced. Okay, so this is the probability that x is between A and B. Okay, now we will see very important parameters now. Okay, the mean of the random variable. That means I am going to discuss about the statistical parameters of the random variable. Okay, so before that, for discrete random variable, I told you we have the cumulative distribution function and the probability mass function, and I defined the mean. You remember, I defined the mean summation for all I xi into p of xi. What is this? It is the probability mass function. Okay, but in continuous random variable, instead of probability mass function, we have probability density, sorry, small letter, we have the probability density functions. Okay, so this is PDF. So instead of mass function, actually this is in discrete random variable, and in continuous random variable we have the probability density function. And you know that this is the summation. Okay, and xi is that random variable. Okay, takes the value of this, the value of the random variable. So we can define the mean of the random variable now in continuous random variable as, instead of summation, you see here, instead of summation I am going to use the integration. Okay, and instead of xi, in general I will use x, and instead of the probability mass function I will use my PDF fx of x, and I will sum for all I, means x changes from minus infinity to infinity into dx, and this is nothing but the mean of the random variable, of the continuous random variable. Okay, continuous random variable, this is nothing but the mean of the continuous random variable. Okay, and we will also call this as the expected value of the random variable x. So the expected value means what? Expected value. Okay, this is known as the expected value. What is the expected value? Is nothing but the average or mean, another name, or the DC content of the signal, if you are talking about the signal processing, DC content. Okay, so this is the mean of the random variable. So I have the definition for the mean as expected value of the x. It's also given as mu x. Okay, which is nothing but integral minus infinity to infinity x into fx of x dx. Okay, this is the mean of the random variable. Now you can easily find what will be the variance of the random variable. Okay, now I will define about the variance of the random variable x, variance, okay, of the continuous random variable. Okay, continuous random variable. So the variance, I told you, it is the deviation from the mean. What was our formula for discrete random variable? For discrete random variable, sigma x square was summation for all I, then it's xi minus mu x the whole square into px of xi. You see, I will use the same convention. You see here in continuous random variable, I will use, instead of this summation, I will use the integration. Then I have, instead of xi, I have x, and this is mu x. I will take the square, and instead of this pxi, I have the density function fx. Okay, so this is nothing but the definition for the variance of the discrete random variable. Then I will talk about the standard deviation. Okay, the standard deviation. What do you mean by standard deviation? The standard deviation is nothing but the square root of sigma x square. That means the square root of variance, which is nothing but sigma x. That means here it's minus infinity to infinity. So square root of minus infinity to infinity x minus mu x the square into fx dx. Okay, fx of x dx. So this is the standard deviation. Okay, now I will talk about one more thing here. It's mean square value. Mean square value, okay, is basically in signal processing. In signal processing, it's very important. In signal processing, mean square value, you might have already heard about it. So in signal processing, the mean square value means it's the power associated with the signal. It's nothing but the power associated with the signal. Okay, the mean square value. Okay, so what is the mean square value? Mean square value for the discrete random variable, I will talk about the discrete random variable. It is summation for all I. It's the power. Power means if you have a voltage or a current, how to find the power? Power is the square of the voltage or current. That means if you have a random variable x, I, then you have to square it. Then it's nothing but px of xi. Averaging means you have to multiply with the probability and sum it. So this is nothing but the mean square value. Mean square value, we will also call it as expected value of x square. So this is the case for the discrete random variable. Now for the continuous random variable, the expected value of x square is nothing but instead of summation, I will use the integration. So x square fx of x dx, I will integrate from minus infinity to infinity. So I want to introduce you this idea. Expectation means what? Expectation means you are integrating or summing. Okay, you are integrating or summing by multiplying with the PDF or the probability mass function. Okay, this is the case of the discrete random variable, and this is the case of the continuous random variable. So I can write all these things, the above things, like I can conclude all these things. So this is mean. A mean is nothing but the expected value of the random variable x. How to find the expected value? You just see here, you have x and you multiply with fx of x dx, then integrate minus infinity. Now what is this mean square value? Mean square value, I told you about the power of the signal. Okay, mean square value means it's nothing but the expected value of x square. What it is? Expected value of x square is integral minus infinity to infinity. You see here it is x square, so I will use x square, then fx of x dx. Okay, then what is the variance? Sigma x square, it's nothing but expected value of x minus mu x the square. Okay, you see here I have used x minus mu x, so I will use x minus mu x and I will square it. Okay, then I will multiply with fx of x and I will integrate from minus infinity to infinity. Now we can elaborate more on this. Okay, we can elaborate more on this. Expected value of x minus mu x the square is nothing but expected value of, you know that a minus b whole square is a square minus, so minus 2 into a into b, like this, 2 into x into mu x minus, not minus, plus mu x square. Okay, so this is nothing but expected value of x square minus expected value of, this is 2 into expected value of x into mu x, because this 2 and this mu x are constant. They are just some numbers, because mu x is a constant. I told you this is mu x, it will be a constant, because after integration you will get a constant value. Now plus expected value of mu x square. Okay, mu x square. What is this expected value of mu x square? Mu x is a constant, so mu x square is also constant, so the expected value is mu x square itself. So the expected value is mu x square itself. So you will get here as this, you will get as expected value of x square is nothing but x square. Okay, and expected value of x, what is expected value of x? This is nothing but the expected value of x is mu x, so it's mu x. So this guy is mu x, and you have mu x into mu x, this is mu x, so mu x into mu x is mu x square, so minus 2 mu x square, then again a plus mu x square. So what is this? It is nothing but expected value of x square minus mu x square. Okay, this is nothing but the variance. So the expected value of x minus mu x the square is nothing but the expected value of square x square minus mu x square. Okay, and what is this mu x? Mu x is nothing but expected value of x. So mu x square is nothing but expected value of x, you have to square it. Okay, so expected value of x minus mu x the square is nothing but expected value of x square minus expected value of x, you have to square it. Okay, and what is this? It is nothing but the variance. Okay, so this is nothing but the variance. Okay, so the variance, I will again write this equation. Variance is nothing but expected value of x square minus expected value of x the whole square. Okay, so this is the equation for the variance. Okay, I hope this is clear to you. Okay, now there is one more concept which is nothing but the nth order moment of the random variable. The nth order moment of the random variable, this is also an important concept. The nth order moment. Okay, so expected value of x power n, it is nothing but the expected value of x power n. So this is nothing but, that is known as the nth order moment. So it is nothing but integral minus infinity to infinity. Since you have used capital X power n, you have to use here small x power n into fx of x dx. But in case of discrete random variable, you can use summation. Okay, so in discrete random variable also, this is the case of continuous random variable. In discrete random variable case, expected value of x power n is nothing but, instead of integration you have to sum it for all I xi raised to n, then px of xi. This is the probability mass function. Okay, and this is the probability density function in continuous. So this is the discrete random variable case. Okay, now what will be our mean square value? Mean square value is nothing but expected value of x square. That means in this case actually n equal to 2. So if n equal to 2, then the moment is called mean square value, right? It's this moment is nothing but the mean square value. Okay, that's it. So we will continue our discussion on this by doing the problem in the next lecture. Okay, thank you.